Finally, let's look at the common mistakes, the bugs that turn up again and again when you build these graphs. This is the most common bug with an adjacency matrix. The edge is undirected, so it should live in two cells. But the buggy add edge sets only M at row U, column V, and forgets M at row V, column U. Now the graph quietly acts as if it were directed. A search that starts at V never finds the edge back to U, so it can miss whole parts of the graph. This is the line that does the right. It sets G arrow matrix at index U times G arrow N plus V to 1. That marks the edge in one direction only. This comment marks the line that is missing. The second right, into M at row V, column U, was never added. The fix is simple. Always write both cells for an undirected edge and never skip the second one. A quick learning check. We call add edge matrix buggy with 1 and 4. Then we ask two questions. What does has edge matrix of 4 and 1 return? And what does has edge matrix of 1 and 4 return? Pause before the reveal. Here is the answer. Has edge of 4 and 1 returns 0 because the mirror cell was never set. Has edge of 1 and 4 returns 1. The same undirected edge answers differently depending on which side you ask it from. The matrix bug is not the only one. This table lists two more bugs that come from the representation itself. The left column names the bug, the middle column is the symptom, and the right column is the fix. The first one is the list version of the same mistake. You push the edge onto only one endpoint's chain. The symptom is the same asymmetry as the matrix bug. The edge is invisible from the other vertex. The fix is to always push onto both edge at index U and edge at index V. The second one is the self loop, an edge from a vertex to itself. A self loop correctly adds 2 to the degree of U because it has two ends. But this course uses simple graphs, which do not allow loops. So the fix is that add edge must reject the case where U equals V. This course's example graph has no self loops.